Subscribe to the channel so you don't miss out on any of these videos. Imagine this. Light, the fastest thing in the universe, doesn't travel in a straight line. Instead, it bends, twists, and distorts like a mirage in the desert. But what could possibly make light do that? What invisible force is powerful enough to warp the very fabric of space itself? The answer lies in one of the most mind-bending phenomena in all of astrophysics: gravitational lensing. It's not just some abstract theory or scientific curiosity. Gravitational lensing is like having a cosmic magnifying glass that reveals secrets of the universe we could never see otherwise. From uncovering ancient galaxies to piecing together the dark puzzle of dark matter, this phenomenon changes how we see and understand the cosmos. So, what exactly is gravitational lensing, and why does it matter? At its core, it's based on a simple yet profound idea. Gravity doesn't just pull objects together. It also warps the fabric of space itself. When a massive object like a galaxy cluster or a black hole sits in space, it creates a kind of dent or curve in the invisible fabric that makes up the universe. And when light from a distant star or galaxy passes near this curve, it doesn't travel in a straight path. Instead, it follows the curve, bending around the massive object. What we end up seeing from Earth is a distorted, magnified, or even duplicated version of the distant object, almost like looking through a funhouse mirror. But gravitational lensing isn't just about bending light for fun. It's one of the most powerful tools astronomers have to uncover the mysteries of the universe. For starters, it lets us peer into the depths of space in a way we otherwise couldn't. Some galaxies are so far away that their light is impossibly faint and would be invisible to even our most advanced telescopes. But if there's a massive object between us and that distant galaxy, its gravitational field acts as a lens, amplifying the light and making the galaxy visible. This allows astronomers to study parts of the universe that are billions of light years away, places that existed when the universe was still young. The story of gravitational lensing starts with Albert Einstein and his groundbreaking theory of general relativity. Back in 1915, Einstein proposed that massive objects warp the space around them, much like a heavy ball placed on a stretched rubber sheet. But it wasn't until 1919 that this idea was confirmed during a solar eclipse. Scientists observed that stars near the edge of the sun appeared to shift slightly from their expected positions, as their light was bent by the sun's gravitational field. This was the first observational proof of gravitational lensing, and a dramatic confirmation of Einstein's theory. Fast forward to today, and gravitational lensing has become a cornerstone of modern astrophysics. There are three main types of gravitational lensing: strong lensing, weak lensing, and microlensing. Each one reveals a different layer of the universe's secrets. Strong lensing happens when the alignment between the distant object, the massive lensing object, and the observer is almost perfect. This can create spectacular visual effects like Einstein rings, circular arcs of light, or multiple images of the same galaxy. Weak lensing, on the other hand, involves more subtle distortions in the shapes of galaxies. By studying these distortions across large areas of the sky, astronomers can map the distribution of dark matter, the mysterious substance that makes up most of the universe's mass. Finally, microlensing occurs on much smaller scales, often involving stars or planets, and has been used to detect planets in other solar systems. What makes gravitational lensing even more fascinating is how it helps us tackle some of the biggest cosmic mysteries. Take dark matter, for example. This elusive substance doesn't emit, absorb, or reflect light, making it invisible to traditional methods of observation. But dark matter does have mass, which means it can bend light through gravitational lensing. By analyzing how light from distant galaxies is distorted as it passes through regions of space filled with dark matter, scientists can map out where dark matter is and how it's distributed. This has led to some of the most detailed and mind-blowing maps of the universe's invisible scaffolding. Gravitational lensing is also a time machine of sorts. Because light takes time to travel across the universe, the light we see from distant galaxies shows us what they looked like billions of years ago. In some cases, gravitational lensing allows us to see galaxies that existed just a few 100 million years after the Big Bang, offering invaluable clues about the universe's early days. Without lensing, many of these ancient galaxies would remain forever hidden from view. But the story doesn't end there. Gravitational lensing also plays a crucial role in testing fundamental physics. For instance, it's used to measure the Hubble constant, which describes how fast the universe is expanding. By studying the time delays between different images of the same lensed object, astronomers can refine their measurements of cosmic expansion and address one of the biggest controversies in modern cosmology. Perhaps the most thrilling aspect of gravitational lensing is that it's still revealing surprises. New discoveries are being made all the time, from finding ultra-distant quasars to uncovering hidden galaxies cloaked in darkness. Some scientists even speculate that gravitational lensing could help us detect the presence of exotic phenomena like primordial black holes or even wormholes, hypothetical shortcuts through space and time. Gravitational lensing isn't just a phenomenon, it's a cosmic detective tool, a time machine, and a magnifying glass rolled into one. It's proof that the universe is far stranger and more interconnected than we could ever imagine. And as our telescopes get more powerful and our understanding of physics deepens, who knows what other mysteries gravitational lensing will help us uncover? What's clear is that this fascinating phenomenon is key to unlocking some of the deepest questions about the cosmos and our place within it. The power of gravitational lensing lies not just in its ability to bend light, but in how it bends our understanding of the cosmos. Think about this: every time light is distorted, it tells a story. It speaks of massive galaxy clusters that hold unimaginable weight, of invisible structures made of dark matter, and of the universe's relentless expansion. And yet, we've only begun to scratch the surface of what gravitational lensing can teach us. Let's delve deeper into strong gravitational lensing. This is the kind that creates dramatic, almost surreal images, rings of light that look like cosmic halos, arcs that stretch across the blackness of space, and multiple images of the same object that seem to defy logic. These stunning visual phenomena occur because the alignment between the observer, the lensing mass, and the distant light source is nearly perfect. When this alignment happens, light from the background object is bent so severely that it forms a complete ring of light around the lensing object, known as an Einstein ring. Einstein rings are not just visually striking, they are also treasure troves of information. By studying the size, shape, and brightness of these rings, astronomers can determine the mass and composition of the lensing object. This includes not just visible matter like stars and gas, but also dark matter, which otherwise evades detection. Einstein rings essentially act as a fingerprint for the lensing object, revealing details that would otherwise be impossible to observe. Beyond the aesthetic beauty of strong lensing, there's a practical side to it that is equally compelling. For instance, strong lensing has been used to observe supernovae, exploding stars whose light can take multiple paths around the lensing object. These multiple paths mean that light from the same event can reach Earth at different times. Imagine seeing a supernova today and then seeing another image of the same supernova months or even years later, simply because the light traveled a longer route around the lensing mass. This time delay effect isn't just a fascinating quirk, it's a tool that allows scientists to study the rate at which the universe is expanding. Weak gravitational lensing, while less dramatic visually, is no less important scientifically. This type of lensing creates subtle distortions in the shapes of background galaxies, almost like a smudge on a cosmic painting. These distortions might seem insignificant at first glance, but when observed on a large scale, they reveal a hidden pattern, a map of the universe's underlying structure. Weak lensing surveys, such as those conducted by the Hubble Space Telescope, have been instrumental in constructing detailed maps of dark matter distribution. These maps show that dark matter isn't evenly spread across the universe. Instead, it clumps together in massive filaments and clusters, forming a kind of cosmic web. This cosmic web is more than just a fascinating visual, it's a key to understanding how galaxies form and evolve. Dark matter acts as the scaffolding for the universe, providing the gravitational pull that helps gas and dust coalesce into stars and galaxies. Without dark matter, the universe as we know it wouldn't exist. By studying weak lensing, scientists can trace the growth of this scaffolding over time, piecing together a story that stretches back billions of years. Microlensing, the third type of gravitational lensing, operates on a much smaller scale but is no less revolutionary. Instead of focusing on galaxy clusters or massive black holes, microlensing examines individual stars and planets. When a star or planet passes in front of a more distant light source, its gravitational field briefly magnifies the light, creating a temporary brightening that can last days or weeks. This technique has been incredibly useful for discovering exoplanets, planets that orbit stars outside our solar system. In fact, some of the most unusual exoplanets, including rogue planets that drift through space without a host star, have been discovered using microlensing. What's remarkable about microlensing is its ability to detect planets that other methods, like the transit or radial velocity techniques, might miss. For example, microlensing can spot planets that are far from their host stars, in orbits where it would be nearly impossible to detect them otherwise. It can also reveal planets and systems where the stars are too faint or too distant to study directly. In this way, microlensing expands our understanding of planetary diversity and offers a glimpse into the vast array of worlds that populate our galaxy. Now, let's talk about the role gravitational lensing plays in uncovering the early universe. One of the biggest challenges in cosmology is observing the first galaxies that formed after the Big Bang. These galaxies are incredibly faint, and their light has been stretched into the infrared by the universe's expansion. This makes them difficult to detect, even with the most advanced telescopes. But gravitational lensing provides a solution. By amplifying the light from these early galaxies, lensing makes it possible to study their properties in detail. This has led to groundbreaking discoveries about how the first stars and galaxies formed, how they interacted with their environments, and how they influenced the evolution of the universe. Gravitational lensing also offers a unique window into the nature of dark energy, the mysterious force that drives the universe's accelerated expansion. By studying how lensing patterns change over time, scientists can measure how the distribution of matter evolves and how the expansion of the universe affects the curvature of space. This, in turn, provides crucial clues about the properties of dark energy and its role in shaping the cosmos. What's even more exciting is how gravitational lensing could help us discover entirely new phenomena. For instance, some theories suggest that lensing could reveal the presence of primordial black holes, tiny black holes that might have formed in the early universe. These black holes are thought to be candidates for dark matter, and their detection would revolutionize our understanding of both dark matter and the origins of the universe. Similarly, lensing could potentially uncover evidence of exotic objects like cosmic strings or wormholes, offering tantalizing hints of physics beyond our current understanding. And yet, for all its power, gravitational lensing remains a frontier of exploration. New telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are expected to push the boundaries of what we can learn from lensing. With their unprecedented sensitivity and resolution, these instruments will enable scientists to study lensing in greater detail than ever before, opening up new avenues for discovery. Gravitational lensing is more than just a tool for astronomy. It's a gateway to the universe's most profound mysteries. It reveals the unseen, illuminates the distant, and challenges our perceptions of reality. In bending light, it bends our understanding, forcing us to see the cosmos not as a static backdrop but as a dynamic, interconnected tapestry where every photon carries a story. And as we continue to study this phenomenon, one thing is certain: gravitational lensing will remain one of our most powerful and awe-inspiring tools for exploring the universe. Gravitational lensing also challenges us to think beyond the visible universe and grapple with the unseen forces that shape it. The phenomenon itself wouldn't exist without the profound influence of dark matter. While dark matter doesn't emit, absorb, or reflect light, its gravitational pull is evident through the way it bends light via gravitational lensing. This invisible component of the cosmos is far more abundant than regular matter, making up an estimated 85% of the universe's total mass. But what exactly is dark matter? That question has baffled scientists for decades, and gravitational lensing serves as one of the most effective tools for probing this enigmatic substance. By observing lensing effects, astronomers can map out the dark matter's distribution across galaxy clusters and the wider cosmos. These maps reveal that dark matter forms massive clumps, acting like scaffolding around which galaxies are arranged. Without dark matter's gravitational influence, the large-scale structure of the universe would be vastly different, if it even existed at all. Consider the bullet cluster, one of the most famous cases in astrophysics. When two galaxy clusters collided, their visible matter, stars and gas, behaved differently from the dark matter. The hot gas, which makes up most of the ordinary matter in the clusters, slowed down and heated up due to friction, while the dark matter passed through unimpeded. Gravitational lensing observations of the bullet cluster clearly show the separation between these two components, providing some of the most compelling evidence for the existence of dark matter. However, the study of dark matter through gravitational lensing isn't limited to galaxy clusters. Weak lensing surveys have allowed scientists to examine the dark matter distribution on cosmic scales, helping to refine models of how the universe evolved. These surveys use subtle distortions in the shapes of millions of background galaxies to infer the large-scale structure of dark matter. The results paint a picture of a universe dominated by dark matter, with ordinary matter making up only a small fraction of the total mass. Gravitational lensing has also revealed peculiar phenomena that hint at the possibility of new physics. For example, some lensing observations don't match the predictions made by existing models of dark matter. These discrepancies have led to speculation about alternative theories, such as the existence of warm dark matter, as opposed to cold dark matter, or even modifications to the laws of gravity. While these ideas are still being tested, they highlight how gravitational lensing continually pushes the boundaries of our understanding. Beyond dark matter, gravitational lensing plays a crucial role in uncovering the nature of dark energy, the mysterious force responsible for the accelerated expansion of the universe. By analyzing lensing patterns over vast cosmic distances, scientists can study how the expansion rate of the universe has changed over time. This provides essential data for understanding dark energy's properties, such as its density and its potential to vary across time and space. One way this is done is through cosmic shear, a type of weak gravitational lensing that looks at the very slight distortions in the shapes of galaxies. By examining how these distortions vary with distance, astronomers can infer how the universe's expansion has affected the distribution of matter over billions of years. This, in turn, offers insights into how dark energy operates, providing critical clues about the fate of the universe. Interestingly, gravitational lensing also allows us to test some of the most ambitious theories in physics, including string theory and the possibility of extra dimensions. Certain predictions made by these theories, such as the existence of exotic objects like cosmic strings, could potentially be observed through their lensing effects. Cosmic strings, for instance, are hypothetical defects in the fabric of SpaceTime that could bend light in highly distinctive ways. Detecting these features would provide groundbreaking evidence for physics beyond the standard model. The future of gravitational lensing research looks incredibly promising, thanks in large part to advancements in telescope technology. The James Webb Space Telescope, JWST, launched in December 2021, is already making strides in observing the universe's earliest galaxies through gravitational lensing. Its powerful infrared capabilities allow it to peer through cosmic dust and capture the faint light from objects billions of light-years away. This has opened a new chapter in our understanding of how galaxies formed and evolved in the universe's infancy. Meanwhile, the upcoming Nancy Grace Roman Space Telescope, expected to launch in the mid-2020s, is designed specifically for wide-field surveys of the sky. This telescope will provide unparalleled data on weak gravitational lensing, enabling scientists to create the most detailed maps of dark matter ever produced. The Roman telescope will also study time-delayed strong lensing events, offering new insights into the expansion rate of the universe and the properties of dark energy. Gravitational lensing doesn't just provide answers, it raises profound questions. What does it tell us about the true nature of gravity? Einstein's general theory of relativity, which predicts gravitational lensing, has been remarkably successful in describing the large-scale structure of the universe. But some lensing observations suggest that there might be more to the story. For instance, certain anomalies in lensing data have led scientists to wonder if our understanding of gravity might need revising or expanding. Furthermore, gravitational lensing could potentially reveal the existence of new types of particles or forces. Some theories propose that lensing effects might be influenced by yet undiscovered particles that interact only through gravity. Detecting such particles would revolutionize our understanding of the universe at its most fundamental level. The philosophical implications of gravitational lensing are equally profound. It forces us to confront the vastness and complexity of the universe, as well as our own place within it. The fact that light can be bent and manipulated on such grand scales challenges our perception of reality, and underscores the interconnectedness of everything in the cosmos. Every photon of light that reaches us, every lensing event we observe, is a reminder of the intricate dance of forces and matter that shape the universe. And yet, for all its scientific importance, gravitational lensing also has a poetic quality. It transforms the cosmos into a hall of mirrors, where light travels paths we can barely comprehend, creating images that are as beautiful as they are enigmatic. It reveals the universe not just as a collection of stars and galaxies, but as a dynamic, living system where every particle of matter and every ray of light plays a role. As we continue to explore the phenomenon of gravitational lensing, one thing is clear: it is a gift that keeps on giving. It deepens our understanding of the universe, challenges our assumptions, and inspires us to ask bigger and bolder questions. In bending light, gravitational lensing bends our minds, expanding our horizons and inviting us to see the cosmos in ways we never thought possible. Gravitational lensing not only provides an extraordinary window into the universe's vastness, but it also bridges the gap between theoretical predictions and observable phenomena. It is a perfect blend of Einstein's abstract equations and the tangible proof astronomers can gather with telescopes. This harmony between theory and observation is what makes gravitational lensing one of the most compelling aspects of modern astrophysics. The story of gravitational lensing begins with the concept of space-time curvature. Einstein's general theory of relativity fundamentally changed the way we view gravity. Before Einstein, gravity was understood as a force pulling two objects toward one another, as Newton described. Einstein reframed gravity as the warping of spacetime caused by massive objects. In this view, the Earth doesn't orbit the Sun because of a force pulling it inward, but because the Sun's immense mass creates a curve in the fabric of spacetime, and Earth follows that curve. Gravitational lensing takes this idea a step further by showing us how light behaves in this curved space. Light, although massless, follows the curvature of spacetime created by massive objects. Imagine placing a marble on a stretched rubber sheet with a heavy ball in the center. The marble's path bends as it rolls near the ball due to the dip in the sheet. Similarly, light bends when it travels close to a massive object like a galaxy or a black hole. This bending of light isn't just a theoretical curiosity, it's observable and measurable. The first evidence of this phenomenon came in 1919 during a solar eclipse. Astronomers measured the apparent positions of stars near the Sun's edge and found they were shifted slightly outward, as predicted by Einstein's equations. This was one of the first major confirmations of general relativity, and catapulted Einstein to global fame. Fast forward to the modern day, and we now use gravitational lensing to peer into the most distant reaches of the cosmos. When light from a distant galaxy or quasar passes near a massive object like a galaxy cluster on its way to Earth, it gets bent and magnified. This process can produce multiple images of the same object, magnify faint light, or even create stunning patterns like Einstein rings, where the light forms a perfect circle around the lensing mass. These effects are not just beautiful, they're invaluable tools for scientific discovery. Einstein rings, in particular, are an exquisite demonstration of the universe's elegance and complexity. They occur when the source of light, the lensing mass, and the observer are perfectly aligned. This perfect alignment is rare, but when it happens, the result is a mesmerizing halo of light. Einstein rings serve as natural laboratories, allowing astronomers to study both the lens source and the lensing mass in unprecedented detail. One of the most fascinating aspects of gravitational lensing is its ability to act as a natural telescope, magnifying objects that would otherwise be too faint or distant to observe. This technique, known as strong gravitational lensing, has enabled astronomers to study the earliest galaxies formed after the Big Bang. By analyzing the light from these ancient galaxies, scientists can gain insights into how stars and galaxies formed in the universe's infancy. But gravitational lensing isn't limited to studying distant galaxies. It also plays a critical role in understanding compact, enigmatic objects like black holes and neutron stars. These objects, with their immense gravitational fields, produce extreme lensing effects that can reveal their properties. For example, light passing close to a black hole can be bent so severely that it creates a phenomenon known as gravitational mirage, where multiple distorted images of the same light source appear around the black hole. The study of microlensing, a specific type of gravitational lensing, has also opened up new avenues in astronomy. Unlike strong lensing, where the lensing mass is a galaxy or a cluster, microlensing occurs when a single star or planetary object acts as the lens. This subtle bending of light can be used to detect exoplanets orbiting stars in distant parts of the galaxy. Microlensing events are fleeting, lasting days or weeks, but they provide critical data about planets that are otherwise difficult to detect. Microlensing is particularly useful for finding planets in regions of the galaxy where other detection methods, like the transit method or radial velocity, struggle to work. It has even been used to discover rogue planets, planetary bodies not bound to any star, wandering through the galaxy. These discoveries have profound implications for our understanding of planetary formation and the diversity of planetary systems. The use of gravitational lensing to study dark matter has also sparked innovative approaches in astrophysics. While we cannot see dark matter directly, its presence can be inferred from its gravitational effects on visible matter. Gravitational lensing provides a direct way to map out the distribution of dark matter, offering a clearer picture of its role in shaping the universe's structure. For instance, scientists use weak gravitational lensing to study the large-scale distribution of dark matter. By analyzing the subtle distortions in the shapes of millions of background galaxies, they can create detailed maps of dark matter's distribution. These maps have revealed that dark matter forms a vast cosmic web, with dense regions corresponding to galaxy clusters and voids where there is little matter. Gravitational lensing also allows for the detection of dark matter clumps within galaxy clusters that might otherwise go unnoticed. These clumps, often too small to contain significant amounts of visible matter, are critical for testing theories about the nature of dark matter. Some models predict that dark matter should form clumps at all scales, while others suggest it might be more diffuse. Observations of gravitational lensing help refine these models, bringing us closer to understanding this mysterious component of the universe. The potential for gravitational lensing to uncover new physics is immense. Some scientists speculate that anomalies in lensing data could point to alternative theories of gravity, such as modifications to general relativity or the existence of additional dimensions. These ideas are still highly speculative, but they underscore how gravitational lensing serves as a gateway to exploring uncharted territories in physics. Moreover, gravitational lensing is a tool for testing fundamental cosmological parameters. By studying the lensing effects on light from distant supernovae and quasars, astronomers can measure the expansion rate of the universe with unprecedented precision. This has implications for understanding dark energy, the mysterious force driving the universe's accelerated expansion. Gravitational lensing, in essence, connects the smallest scales of physics to the largest scales of cosmology. It is a testament to the interconnectedness of the universe and the power of human curiosity to unravel its mysteries. Every lensing event, every distorted image of a distant galaxy, is a clue in the ongoing quest to understand the cosmos. The relationship between gravitational lensing and the quest to understand dark energy is particularly intriguing. Dark energy, which makes up about 68% of the universe, remains one of the greatest enigmas in cosmology. Its existence was inferred from the observation that the universe's expansion is accelerating, but its nature is still largely unknown. Gravitational lensing provides a way to probe this mysterious force by offering precise measurements of cosmic expansion. When light from distant objects passes through a lensing mass, its path and travel time are affected by the curvature of SpaceTime. By analyzing these distortions, astronomers can determine how much the universe has expanded since the light left its source. This information is crucial for constraining models of dark energy and understanding its influence on the cosmos. A key technique in this effort is time delay cosmography. In some cases of strong gravitational lensing, such as when a galaxy or quasar is lensed, multiple images of the same object are created. These images often have slight differences in brightness and appearance due to the varying paths the light takes around the lensing mass. Crucially, the time it takes for light to travel along these paths can also differ, a phenomenon known as the time delay. By carefully measuring these time delays and combining them with detailed models of the lensing mass, astronomers can estimate the Hubble constant, which describes the rate of the universe's expansion. This method is independent of other techniques, such as observations of the cosmic microwave background or type Ia supernovae, and provides a valuable cross-check for these measurements. Discrepancies in the values of the Hubble constant obtained through different methods have sparked intense debate in the scientific community, and gravitational lensing has played a central role in this ongoing discussion. Beyond its cosmological implications, gravitational lensing is also a powerful tool for studying the properties of individual galaxies and galaxy clusters. For example, it allows astronomers to probe the distribution of mass within these structures, including the invisible dark matter component. This is particularly important for understanding how galaxies and clusters form and evolve over cosmic time. Galaxy clusters, the largest gravitationally bound structures in the universe, are excellent laboratories for studying gravitational lensing. Their immense mass, dominated by dark matter, creates strong lensing effects that magnify and distort the images of background galaxies. These lensing patterns can be used to map the distribution of dark matter within the cluster with remarkable precision. One famous example is the galaxy cluster Abell 1689, which has produced some of the most detailed maps of dark matter ever created. By analyzing the lensing effects on hundreds of background galaxies, astronomers were able to construct a three-dimensional map of the cluster's dark matter distribution. Such studies reveal how dark matter is concentrated within clusters and provide insights into its interaction with ordinary matter. Gravitational lensing also sheds light on the elusive properties of black holes, which are among the universe's most enigmatic objects. When light from a background star or galaxy passes near a black hole, it experiences extreme bending due to the black hole's intense gravitational field. This can create phenomena like relativistic beaming, where light is magnified and focused into narrow paths, and photon rings, which are the result of light circling the black hole multiple times before escaping. These effects are not only visually stunning but also scientifically valuable. They offer a way to study the event horizon, the boundary beyond which nothing can escape a black hole's gravity. Observations of gravitational lensing near black holes have even been used to test the Noether theorem, which predicts that black holes can be fully described by just three parameters: mass, charge, and spin. Perhaps even more fascinating is the role of gravitational lensing in the search for primordial black holes. These hypothetical black holes, which may have formed in the early universe, are potential candidates for dark matter. If they exist, their presence could be revealed through microlensing events, where their gravity temporarily magnifies the light from a background star. While the evidence for primordial black holes remains inconclusive, gravitational lensing offers a promising avenue for their detection. The interplay between gravitational lensing and exoplanet research is another area of active exploration. Microlensing events, where a star or planet briefly magnifies the light of a background object, have been used to detect planets in regions of the galaxy that are difficult to study with other methods. Unlike the transit method, which requires the planet to pass directly in front of its host star, or radial velocity, which measures the star's wobble caused by a planet's gravity, microlensing can detect planets regardless of their orientation or distance from the host star. One of the most intriguing findings from microlensing surveys is the discovery of rogue planets, planetary bodies that are not gravitationally bound to any star. These free-floating planets are thought to have been ejected from their original systems and now wander through the galaxy alone. Detecting rogue planets is incredibly challenging, but microlensing provides a unique way to identify them. These discoveries challenge traditional notions of planetary formation and raise fascinating questions about the abundance and diversity of planets in the universe. Gravitational lensing also plays a pivotal role in the study of the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. By analyzing the weak lensing effects on the light from distant galaxies, astronomers can map the distribution of dark matter on cosmic scales. These maps reveal the intricate patterns of the cosmic web, with dense regions corresponding to galaxy clusters and sprawling voids where matter is scarce. Weak lensing studies have also provided some of the strongest evidence for the existence of dark energy. By comparing the observed distribution of matter with theoretical predictions, scientists have shown that the universe's expansion is accelerating. This acceleration can only be explained by the presence of dark energy, making gravitational lensing a crucial tool for understanding the forces shaping the cosmos. The future of gravitational lensing research holds immense promise. Upcoming telescopes and observatories, such as the James Webb Space Telescope, JWST, the Vera C. Rubin Observatory, and the European Space Agency's Euclid mission, are poised to revolutionize our understanding of lensing phenomena. These instruments will provide high-resolution images and deeper surveys, allowing astronomers to study lensing effects in greater detail and uncover new phenomena. The Euclid mission, in particular, aims to map the geometry of the dark universe by studying weak gravitational lensing and galaxy clustering. Its findings are expected to shed light on the nature of dark energy and refine our understanding of dark matter's role in cosmic evolution. Similarly, the Rubin Observatory's Legacy Survey of Space and Time, LSST, will produce an unprecedented catalog of gravitational lensing events, enabling a wide range of scientific investigations. Gravitational lensing is a testament to the power of human ingenuity and the relentless drive to explore the unknown. It transforms the universe into a cosmic lens, offering a unique perspective on its deepest mysteries. From the bending of starlight near the sun to the intricate patterns of the cosmic web, gravitational lensing connects us to the fabric of space-time and the forces that govern it. Gravitational lensing is more than just a phenomenon. It is a bridge between the seen and the unseen, the known and the unknown. It invites us to look beyond the surface, to peer into the depths of the cosmos, and to unravel the secrets of the universe one bent ray of light at a time. Gravitational lensing remains one of the most compelling tools for investigating the universe's invisible components. Its potential for uncovering new insights is far from exhausted, and as technology advances, so too will our ability to utilize this cosmic phenomenon. One particularly exciting avenue of future research is the application of lensing to study the epoch of reionization, a period in the universe's history when the first stars and galaxies formed, reionizing the intergalactic medium. This era is notoriously difficult to study directly because the light from these early objects is faint and redshifted due to the expansion of the universe. However, gravitational lensing can magnify these ancient signals, providing a rare glimpse into the universe's formative stages. By combining lensing observations with the capabilities of next-generation telescopes like the JWST, astronomers hope to identify some of the first galaxies and understand how they influence the surrounding environment. Another frontier in gravitational lensing research lies in the detection of intermediate-mass black holes. While stellar mass and supermassive black holes are well documented, intermediate-mass black holes, with masses between 100 and 100,000 times that of the Sun, remain elusive. Their existence is critical for understanding how supermassive black holes form, as they may represent an evolutionary bridge. Microlensing events caused by these intermediate-mass black holes could reveal their presence. For instance, if an intermediate-mass black hole passes in front of a star, the gravitational lensing effect could magnify the star's light temporarily. Analyzing such events would provide valuable information about the black hole's mass and distribution, contributing to our broader understanding of black hole populations in the universe. In addition to probing individual objects, gravitational lensing also has the potential to explore the nature of exotic phenomena such as cosmic strings. These hypothetical one-dimensional defects in space-time, thought to have formed during the early universe, could produce unique lensing signatures. As light passes near a cosmic string, it would not bend in the same way as with a massive object. Instead, the string would act like a wedge, splitting the light into two parallel paths. Detecting such signatures would not only confirm the existence of cosmic strings but also provide direct evidence for processes that occurred during the universe's infancy. These findings would offer a new perspective on the fundamental physics that govern space-time and the origins of the cosmos. The hunt for axions, hypothetical particles that could solve the mystery of dark matter, also intersects with gravitational lensing research. Axions are predicted to form dense clumps known as axion stars. If these clumps act as lensing masses, they could create subtle distortions in the light from background sources. Observing these effects would represent a groundbreaking discovery, linking the particle physics of dark matter with the large-scale structure of the universe. Gravitational lensing's ability to connect disparate fields of study, from quantum mechanics to cosmology, underscores its importance as a scientific tool. Its applications extend beyond astrophysics, influencing other disciplines such as mathematics, computer science, and even artificial intelligence. For example, the complex task of modeling lensing events has spurred the development of advanced algorithms and machine learning techniques. These tools, in turn, are being adapted for use in medical imaging, data analysis, and other fields. Despite its many successes, gravitational lensing research faces several challenges. Accurately modeling the lensing mass requires precise measurements of the distribution of dark matter and baryonic matter. Any errors or uncertainties in these models can affect the interpretation of lensing data, leading to biases in cosmological parameters such as the Hubble constant or the equation of state for dark energy. To address these challenges, scientists are developing more sophisticated models that incorporate higher-order effects and account for complex structures within lensing masses. Observations from multiple wavelengths, such as optical, infrared, and X-ray, are also being combined to create a more comprehensive picture of lensing systems. These efforts are critical for improving the accuracy and reliability of lensing-based studies. The ethical implications of gravitational lensing research also warrant consideration. As we uncover more about the universe's fundamental nature, we must grapple with the philosophical questions raised by these discoveries. What does it mean to study phenomena that lie beyond human perception? How should we prioritize scientific exploration in the face of pressing global challenges? These questions remind us that science is not conducted in a vacuum but is deeply intertwined with broader societal values and goals. Ultimately, gravitational lensing serves as a powerful reminder of the interconnectedness of the universe. The bending of light by massive objects reveals not only the structure of space-time but also the hidden forces that shape our reality. It demonstrates that even the faintest signals can carry profound information, connecting us to the farthest reaches of the cosmos. As we continue to unravel the mysteries of gravitational lensing, we are also uncovering new questions that demand answers. What lies beyond the observable universe? How do the smallest particles influence the largest structures? And what role does humanity play in the grand tapestry of existence? These are the questions that drive us to look deeper, to push the boundaries of knowledge, and to explore the unknown. Gravitational lensing is a phenomenon that invites us to reimagine our place in the universe. It challenges our perceptions of distance, scale, and the very nature of reality. By bending the paths of light, the universe offers us a means to see beyond what is immediately visible and to uncover secrets buried in its deepest recesses. Yet, even as we make strides in understanding this incredible effect, it becomes evident that the more we uncover, the more there is to explore. One particularly intriguing aspect of gravitational lensing is its role in detecting rogue planets. These are planets that have been ejected from their host star systems and now drift through interstellar space. Because they emit little to no light of their own and are not illuminated by a nearby star, rogue planets are virtually impossible to detect with traditional telescopes. However, microlensing events, in which these wandering planets pass in front of a background star, can temporarily magnify the star's light. This brief brightening provides a unique opportunity to identify and study these solitary worlds. Each rogue planet discovered offers insights into planetary formation and the chaotic dynamics of star systems. In addition to its practical applications, gravitational lensing also serves as a profound metaphor for human curiosity and ingenuity. The light that reaches us after being bent around massive cosmic structures symbolizes the winding paths of discovery that scientists take. It reminds us that indirect evidence can often be more revealing than direct observation, and that persistence and creativity are essential in the pursuit of knowledge. The philosophical implications of gravitational lensing are equally profound. It raises questions about the nature of reality and our ability to perceive it. If light can be bent, distorted, and even split into multiple paths, what does this say about our understanding of the universe? Are the images we see through gravitational lensing a true reflection of reality? Or are they illusions shaped by the fabric of space-time? These questions challenge us to think more deeply about the limits of perception and the nature of truth. Another fascinating application of gravitational lensing is in the study of time. Einstein's theory of general relativity predicts that the bending of light by gravity is accompanied by a stretching of time. This phenomenon, known as gravitational time dilation, means that time moves more slowly in stronger gravitational fields. Observing lensing events allows astronomers to test these predictions and explore the interplay between space and time on a cosmic scale. These studies not only confirm the accuracy of general relativity, but also open new avenues for understanding the fundamental nature of time itself. The future of gravitational lensing research is intertwined with advancements in technology. Upcoming space-based telescopes, such as the Nancy Grace Roman Space Telescope, are expected to revolutionize our ability to observe lensing events. Equipped with wide-field imaging capabilities and advanced spectroscopic instruments, these telescopes will enable astronomers to study thousands of lensing systems in unprecedented detail. This wealth of data will refine our understanding of the distribution of dark matter, the properties of dark energy, and the history of cosmic evolution. In addition to telescopes, artificial intelligence and machine learning are becoming essential tools in gravitational lensing research. These technologies can analyze vast datasets, identify subtle patterns, and model complex systems with remarkable accuracy. For example, neural networks are being trained to recognize lensing features in astronomical images, speeding up the discovery process and reducing the likelihood of false positives. As AI continues to evolve, it will play an increasingly central role in unraveling the mysteries of gravitational lensing. Despite the tremendous progress made in recent years, many challenges remain. One of the most significant is the need for better simulations of lensing systems. Creating accurate models of how light interacts with matter on a cosmic scale requires immense computational power and sophisticated algorithms. These simulations must account for a wide range of variables, from the shapes and distributions of lensing masses to the effects of intergalactic dust on light propagation. Overcoming these challenges will require collaboration across disciplines, bringing together experts in astrophysics, computer science, and mathematics. The study of gravitational lensing also highlights the importance of international cooperation in science. Observing lensing events often requires access to multiple telescopes located around the world, as well as data from space-based observatories. Sharing resources and expertise allows researchers to tackle complex problems and achieve results that would be impossible for any single institution or country to accomplish on its own. This spirit of collaboration reflects the interconnectedness of humanity and our shared quest to understand the universe. As we look to the future, it is clear that gravitational lensing will remain a cornerstone of astrophysical research. Its ability to reveal the invisible, probe the distant, and test the fundamental laws of physics ensures its continued relevance in the decades to come. Whether we are mapping the distribution of dark matter, discovering new exoplanets, or exploring the earliest moments of the universe, gravitational lensing provides a window into the unknown. Ultimately, the story of gravitational lensing is a testament to the power of human ingenuity and the boundless curiosity that drives us to explore the cosmos. It is a story of light bending through space, of distant galaxies brought into focus, and of mysteries waiting to be solved. And as we continue to study this remarkable phenomenon, we are reminded of our own place in the vast, interconnected web of existence, a place defined not by our limitations, but by our endless capacity to wonder and to learn. As gravitational lensing continues to captivate the scientific community, it offers an ever-expanding frontier for exploration. With each new discovery, we find ourselves challenging our preconceived notions of space and time. While the universe may appear to be vast and unchanging, gravitational lensing reminds us that nothing in the cosmos is fixed. Instead, the universe is an intricate tapestry of forces, bending and twisting in ways that we are only just beginning to understand. One of the most groundbreaking aspects of gravitational lensing is its ability to test the fundamental principles of physics. In particular, the phenomenon plays a crucial role in verifying the predictions made by general relativity. Einstein's theory, which describes the interaction of matter and energy with the curvature of spacetime, has undergone rigorous testing since its inception over a century ago. Gravitational lensing offers a natural laboratory for testing the limits of general relativity, allowing us to observe how light behaves under extreme conditions. While general relativity has been confirmed in many scenarios, there are still areas where its predictions are not fully understood, particularly when it comes to objects like black holes and dark matter. By observing gravitational lensing events, scientists are able to probe the effects of intense gravitational fields on light, providing insights into the behavior of objects that we can't directly observe. This is especially important for testing theories of dark matter and dark energy, two of the greatest mysteries in modern physics. Dark matter, in particular, is one of the most elusive substances in the universe. While it accounts for a significant portion of the mass in the cosmos, we have yet to detect it directly. Gravitational lensing allows us to map its distribution by observing how light from distant objects is distorted as it passes through regions of space that are rich in dark matter. By analyzing these distortions, scientists can create detailed maps of dark matter and begin to unravel its properties. This is an essential step in understanding the role that dark matter plays in the formation and evolution of galaxies and galaxy clusters. Similarly, gravitational lensing has become a critical tool in the study of galaxy clusters. These massive structures, which consist of hundreds or even thousands of galaxies bound together by gravity, act as natural lenses, magnifying and distorting the light from more distant galaxies. By observing how the light from these distant objects is bent, astronomers can determine the mass and composition of galaxy clusters, as well as gain insights into their formation and evolution. This technique has already led to the discovery of several previously unknown galaxy clusters, and as our observational capabilities improve, we can expect to uncover many more. One of the most exciting potential applications of gravitational lensing lies in the search for exoplanets. While many exoplanets have been discovered using traditional methods, such as the transit method or radial velocity measurements, gravitational lensing offers a completely different approach. By observing how the light from a distant star is bent as it passes near an exoplanet, astronomers can detect the presence of these faraway worlds. This technique, known as microlensing, is particularly useful for detecting exoplanets that are not part of a traditional star system or those that are located far beyond the reach of current telescopes. As more and more microlensing events are discovered, we are likely to uncover an entirely new class of exoplanets, offering valuable insights into the diversity of planetary systems in the universe. Beyond its role in cosmology, gravitational lensing is also providing a unique perspective on the nature of spacetime itself. Einstein's general theory of relativity predicts that massive objects can warp the fabric of spacetime, causing light to follow curved paths. However, there is still much we do not know about how light behaves in these extreme environments. For example, gravitational lensing has revealed the phenomenon of multiple images, where the light from a single source is bent so much that it appears as several distinct images. These multiple images offer a rare opportunity to study the physics of light in the presence of powerful gravitational fields, and they may eventually provide clues to the nature of space-time singularities and the fabric of the universe itself. At the same time, gravitational lensing has prompted us to think about how we interpret the data that we collect. The process of lensing is not always straightforward. Light can be bent by more than one lensing mass, leading to complicated distortions that require careful analysis. In some cases, the light from distant galaxies may be distorted so much that it appears to form arcs or rings, known as Einstein rings. These features are incredibly useful for studying the properties of the lensing mass, but they can also complicate the interpretation of the data. To address these challenges, scientists are developing new computational methods and advanced algorithms that can help disentangle the various effects and provide more accurate results. In the coming decades, gravitational lensing will likely remain at the forefront of astronomical research. As new telescopes and observational techniques come online, our ability to detect and study lensing events will only improve. Instruments like the James Webb Space Telescope, which is capable of observing distant galaxies in infrared light, will enable us to study gravitational lensing in unprecedented detail. This will provide us with more precise measurements of the universe's expansion rate, the distribution of dark matter, and the nature of the most distant galaxies. The future of gravitational lensing also hinges on the development of more powerful simulations and computational models. As we continue to push the boundaries of our understanding, scientists are using increasingly sophisticated models to simulate the effects of gravitational lensing. These simulations allow researchers to test different theories, predict how light will behave under various conditions, and analyze the impact of lensing on the cosmic microwave background. These simulations are essential for refining our measurements and ensuring that our conclusions are based on accurate data. The role of gravitational lensing in shaping our understanding of the cosmos is undeniable. It has already provided answers to many long-standing questions, from the distribution of dark matter to the structure of galaxy clusters. And as our observational capabilities continue to improve, gravitational lensing will undoubtedly reveal even more secrets about the universe. Whether it is uncovering the first galaxies that formed after the Big Bang, shedding light on the mysterious nature of dark energy, or detecting exoplanets in distant star systems, the potential for discovery is limitless. At its core, gravitational lensing reminds us of the profound interconnectedness of the universe. It shows us that light, even as it travels through the vastness of space, is never truly free. It is shaped, bent, and altered by the presence of massive objects that we may never see directly, but whose effects ripple through the fabric of SpaceTime. This is the power of gravitational lensing. It allows us to see the universe not just as it appears, but as it truly is, shaped by the invisible forces that govern its existence. As we continue to study this remarkable phenomenon, we find ourselves on the precipice of new discoveries that will redefine our understanding of the cosmos. And with each new lensing event, we move one step closer to unlocking the deepest mysteries of the universe. Gravitational lensing continues to inspire awe in both scientists and the public alike, not only because of its role in answering some of the universe's deepest questions but also due to the sense of wonder it brings to the very fabric of reality. The fact that we can use the bending of light to peer into the farthest reaches of the cosmos, observing phenomena that would otherwise be completely hidden from us, demonstrates the ingenuity of modern science and our ever-expanding understanding of the universe. One of the most profound aspects of gravitational lensing is its ability to offer direct evidence for the existence of unseen mass, such as dark matter. The concept of dark matter has puzzled physicists for decades. It was first proposed in the 1930s to explain the observed behavior of galaxies, which appeared to be rotating too quickly to remain gravitationally bound based on the visible matter they contained. Despite this, dark matter has eluded direct detection, making it one of the greatest challenges in modern physics. Gravitational lensing, however, provides us with an indirect method of detecting dark matter by observing how it bends the light coming from distant objects. When light from a far-off galaxy passes through a massive galaxy cluster, the dark matter within the cluster exerts a gravitational influence on the light, causing it to bend. The visible galaxies within the cluster act as a lens, but the dark matter, which is invisible to conventional telescopes, also contributes to this lensing effect. By studying the distortions in the light from the distant galaxy, astronomers can map the distribution of dark matter within the cluster. These maps are invaluable in helping us understand not only the quantity and location of dark matter but also its role in the formation and evolution of cosmic structures. This ability to observe dark matter through gravitational lensing is opening new frontiers in astrophysics. It is providing evidence that dark matter is far more widespread than we previously thought, and that it plays a crucial role in the formation of galaxies. In fact, gravitational lensing has revealed that dark matter is not evenly distributed throughout space. Instead, it tends to concentrate in certain regions, often in the form of large halos surrounding galaxies. These halos are not just a theoretical prediction but a confirmed feature of our universe, thanks to the power of gravitational lensing. Furthermore, gravitational lensing has allowed astronomers to observe galaxies that are billions of light years away, offering a glimpse into the early universe. Because of the immense distances involved, these galaxies are seen as they were in their infancy, providing us with a snapshot of the universe's past. Lensing allows us to study these distant galaxies in greater detail, helping us to understand how galaxies form, evolve, and interact. Some of the most important discoveries in modern astronomy, such as the identification of the most distant galaxy ever observed, have been made possible through the use of gravitational lensing. One of the most exciting aspects of using gravitational lensing in this context is its ability to magnify distant objects. Just as a magnifying glass can bring into focus small, distant objects, gravitational lensing magnifies the light from distant galaxies, allowing us to study them in much greater detail than would otherwise be possible. This effect is especially useful when observing faint or distant objects that would otherwise be too dim to detect. In some cases, gravitational lensing can increase the brightness of these distant galaxies by a factor of 10 or more, making them visible to our telescopes for the first time. The implications of these discoveries extend far beyond simply cataloging distant galaxies. By studying how galaxies behave in the early universe, astronomers can learn about the conditions that led to the formation of our own galaxy, the Milky Way, and others like it. They can also learn more about the mysterious processes that led to the creation of the first stars and the formation of the first supermassive black holes. These findings provide important clues about the conditions that allowed life to evolve on Earth, and may even offer insight into the possibility of life elsewhere in the universe. Gravitational lensing also holds great promise in the search for exoplanets, which are planets that orbit stars outside our solar system. As astronomers discover new ways to detect these distant worlds, gravitational lensing offers a new tool in their toolkit. When light from a distant star passes close to an exoplanet, the planet's gravity can bend the light, creating a temporary brightening effect. This is known as microlensing, and it can reveal the presence of exoplanets that might otherwise go undetected. Microlensing has already led to the discovery of hundreds of exoplanets, and as our ability to detect these events improves, it's likely that we'll uncover even more distant worlds. Another fascinating use of gravitational lensing is in the search for primordial black holes, hypothetical black holes that could have formed in the early universe, shortly after the Big Bang. These black holes are theorized to be much smaller than the stellar mass black holes we observe today, but they could have a significant impact on the universe's structure and evolution. Gravitational lensing can help identify the existence of these elusive objects by detecting the subtle distortions they cause in the light from background stars or galaxies. Though no primordial black holes have been definitively detected, gravitational lensing provides an invaluable tool in the search for these mysterious objects. Gravitational lensing also challenges our understanding of the very nature of space and time. The phenomenon serves as a dramatic reminder that space-time is not a fixed, unchanging backdrop against which objects move. Instead, space-time is a dynamic, flexible entity that can be warped and shaped by the presence of mass and energy. This is a concept that lies at the heart of Einstein's general theory of relativity, which tells us that mass and energy cause space-time to curve, and that the curvature of space-time governs the motion of objects within it. This idea was revolutionary when Einstein first proposed it over a century ago, and gravitational lensing provides direct observational evidence of its validity. The fact that we can observe light being bent by the gravity of distant objects not only confirms Einstein's theory but also deepens our understanding of how the universe works at its most fundamental level. Gravitational lensing is one of the most striking manifestations of the curvature of space-time, offering a vivid illustration of how the universe itself is shaped by the forces of gravity. As we continue to develop more advanced observational tools, the study of gravitational lensing will only become more powerful. With the launch of next-generation telescopes, such as the James Webb Space Telescope, we will be able to observe lensing events in even greater detail, allowing us to uncover the mysteries of the cosmos with unprecedented precision. The ability to study the universe through the lens of space-time curvature will provide insights not only into the nature of dark matter and dark energy, but also into the evolution of the universe itself. Gravitational lensing is a window into the unknown. It allows us to peer into regions of space that would otherwise be invisible, offering us a glimpse into the farthest reaches of the cosmos. It challenges our understanding of light, matter, and the very nature of the universe. Through lensing, we are learning more about the fundamental forces that govern the universe, and with each new discovery, we get closer to answering some of the most profound questions of existence. The future of gravitational lensing is boundless, and the mysteries it will help to uncover may forever change the way we perceive our place in the universe. As we continue to explore the universe through the phenomenon of gravitational lensing, it's important to recognize just how vast the potential for discovery really is. Every time we look at the sky through the lens of space-time, we aren't just observing distant galaxies or stars. We're unveiling a cosmic story that has been unfolding for billions of years. Every event that occurs in the universe, whether it's the formation of a galaxy, the death of a star, or the collision of supermassive black holes, can leave a trace, and gravitational lensing allows us to capture these traces in ways that were once unimaginable. One of the most profound discoveries that gravitational lensing has already provided us with is the identification of so-called Einstein rings. These are circular distortions in the light from distant galaxies that occur when the light passes around a massive object, such as a galaxy cluster, situated between us and the source. These rings form when the light from a distant object is perfectly aligned with the mass acting as the lens, creating a symmetrical, circular shape. Einstein rings are not just fascinating because they confirm the curvature of spacetime, they also allow scientists to measure the mass of the intervening object, even if that object is not visible to our telescopes. Interestingly, Einstein rings also serve as a tool for studying the nature of dark matter. Many of the galaxy clusters that produce these rings contain large amounts of dark matter, which, as we mentioned before, doesn't emit light or radiation. The mass of the dark matter can be inferred from the way it bends the light, and in this way, gravitational lensing offers one of the best methods we have to study dark matter. As astronomers continue to identify new Einstein rings, our understanding of how dark matter is distributed throughout the universe will only grow more detailed. In addition to Einstein rings, another interesting result of gravitational lensing is the phenomenon known as multiple images. When light from a distant galaxy passes through a gravitational lens, the light can take multiple paths around the lensing object, resulting in several copies of the same galaxy appearing in different parts of the sky. These multiple images can provide astronomers with a wealth of information about the lensing object itself. By studying the positions, brightness, and color of these multiple images, scientists can learn more about the properties of the lensing object, including its mass, shape, and structure. The concept of multiple images is particularly intriguing when we consider the role of supermassive black holes in the universe. These black holes are thought to reside at the center of most galaxies, including our own Milky Way, and they exert an enormous gravitational pull. When a supermassive black hole acts as a gravitational lens, it can create multiple images of distant objects, which can help us learn more about the black hole itself. In some cases, the light from distant galaxies can be bent in such a way that it appears as a complete arc around the black hole. These arcs can provide valuable insights into the nature of black holes, their growth, and their influence on the surrounding space-time. Gravitational lensing is not just a tool for observing distant galaxies, however. It also has important applications in the study of our own Milky Way galaxy. By using gravitational lensing, astronomers can observe objects that are located within our own galaxy, such as exoplanets and stellar remnants, in ways that would otherwise be impossible. For example, gravitational lensing has been used to detect rogue planets, planets that do not orbit any star but instead wander freely through space. These planets are incredibly difficult to detect using traditional methods, but when they pass in front of a background star, their gravity can bend the light from that star, revealing their presence. The study of rogue planets is particularly important because it could provide insight into the history of planetary systems. If rogue planets are common in the galaxy, it could mean that many planets were ejected from their parent star systems early in their formation. This could have significant implications for our understanding of planet formation and the dynamics of solar systems. Gravitational lensing gives us the ability to study these elusive objects and improve our models of planetary evolution. Another exciting application of gravitational lensing is its potential to help us understand the large-scale structure of the universe. The distribution of galaxies and clusters of galaxies is not uniform. Instead, it is shaped by the gravitational influence of dark matter. By studying how light is bent by galaxy clusters, astronomers can create detailed maps of the large-scale structure of the universe. These maps allow us to see how galaxies are distributed across vast cosmic distances and how they are influenced by the mysterious force of dark energy. One of the ways gravitational lensing is used to study the large-scale structure is by examining the distortions caused by large cosmic voids, regions of space that contain very few galaxies. These voids are thought to be crucial in understanding the overall shape and expansion of the universe. As light passes through these vast, empty regions, the gravitational effects of the surrounding matter cause distortions that reveal hidden features of the voids. By studying these distortions, scientists can better understand the expansion rate of the universe, the nature of dark energy, and how the universe will continue to evolve over time. Perhaps one of the most thrilling aspects of gravitational lensing is its role in helping us probe the very limits of the universe. We are only beginning to scratch the surface of what lensing can reveal, as we continue to improve our observational capabilities. With the upcoming advancements in space telescopes, like the James Webb Space Telescope and the Extremely Large Telescope, the next decade promises to yield groundbreaking discoveries in the study of gravitational lensing. These advanced instruments will allow us to observe even more distant galaxies, measure the distribution of dark matter with unprecedented accuracy, and look further back in time to study the very first galaxies that formed after the Big Bang. The discoveries made through gravitational lensing have the potential to revolutionize our understanding of the universe. It's not just about understanding the positions and structures of galaxies and other cosmic objects. It's about unraveling the deepest mysteries of space-time itself. As we continue to observe and study the universe through the lens of gravitational lensing, we are not just learning more about distant objects. We are learning more about the very nature of the cosmos, its creation, and its ultimate fate. In many ways, gravitational lensing serves as a reminder of just how much we still have to learn. The universe is filled with hidden wonders that we are only beginning to uncover. With every new discovery, we move closer to answering some of the most profound questions in science. What is dark matter? How did the universe form, and how will it end? What are the true nature and limits of space-time? Gravitational lensing is not just a tool, it's a gateway to new frontiers in astrophysics. And as we continue to peer through this gateway, we will inevitably unlock secrets that have eluded us for centuries. The journey through space and time has only just begun, and with the power of gravitational lensing, we are set to explore the deepest corners of the universe. Every lensing event, every distortion in the fabric of space-time, brings us one step closer to understanding the grand tapestry of the cosmos. As we continue to observe, measure, and interpret these cosmic phenomena, we are learning not just about the universe, but about ourselves, and our place within the infinite expanse of space. Gravitational lensing, in many ways, represents a beautiful paradox. It's a cosmic phenomenon that simultaneously reveals and obscures. The very light we rely on to understand the universe is bent and distorted by the mass of distant objects, shaping our view of the cosmos in unexpected ways. Yet, it is through this bending, this distortion, that we gain some of the most profound insights into the universe's deepest secrets. It's almost as if the universe is playing hide-and-seek, revealing just enough to keep us curious, but not all at once. And this constant revelation through gravitational lensing forces us to rethink everything we know about space, time, and the forces that shape them. As we continue to explore gravitational lensing, one of the most intriguing aspects is the way it has transformed the search for dark matter. We have already touched on how lensing can reveal the mass of invisible objects, but let's take a deeper look at how this phenomenon is becoming a key tool in the study of dark matter, the enigmatic substance that makes up most of the mass in the universe yet does not interact with light or other electromagnetic radiation. Astronomers have long known that galaxies don't contain enough visible matter, stars, gas, and dust, to account for the observed gravitational effects. That's where dark matter comes in. But dark matter itself cannot be observed directly, because it doesn't emit, absorb, or reflect light. Instead, it's detected through its gravitational influence on visible matter. Gravitational lensing is a crucial tool in this effort because it allows scientists to map the distribution of dark matter in galaxy clusters. Imagine that a distant galaxy is located behind a large galaxy cluster. As light from that galaxy passes through the cluster, the gravitational pull from the cluster's mass bends the light, much like the way a magnifying glass bends light. This bending distorts the image of the distant galaxy. By studying these distortions, scientists can map the mass of the galaxy cluster, and crucially, they can separate the mass of the visible matter, like galaxies, from the mass of the dark matter, which doesn't emit light. This process gives us a much clearer picture of how dark matter is distributed in the universe. One of the most famous examples of gravitational lensing revealing dark matter is the observation of the Bullet Cluster, a pair of galaxy clusters that collided. The Bullet Cluster provides one of the clearest visualizations of dark matter ever captured. In this case, gravitational lensing allowed astronomers to separate the visible matter, in the form of galaxies and hot gas, from the dark matter, which was inferred from the way light was bent. The result showed that most of the mass in the Bullet Cluster is not in the visible gas or galaxies, but in a vast, invisible cloud of dark matter. This discovery was groundbreaking because it offered direct evidence for the existence and the distribution of dark matter in a galaxy cluster, something that had previously only been theorized. But gravitational lensing isn't just about revealing the unseen. It also helps astronomers peer deeper into the distant universe, beyond what would normally be possible. By using lensing to study the light from galaxies billions of light years away, scientists can observe these galaxies in much more detail than would otherwise be possible. When a massive galaxy or galaxy cluster acts as a gravitational lens, it magnifies the light from a distant galaxy, creating a kind of cosmic zoom lens. This allows astronomers to study the distant galaxy's shape, size, and even its star formation processes in ways that would normally be impossible with conventional telescopes. For instance, the Hubble Space Telescope has provided some of the most remarkable examples of gravitational lensing, revealing galaxies and stars that are billions of light years away. These lensed galaxies can appear as arcs or multiple images, providing astronomers with detailed information about their composition, their evolution, and the conditions in which they formed. Without gravitational lensing, many of these distant galaxies would remain beyond the reach of even the most advanced instruments. Gravitational lensing also holds the potential to help us understand the early universe. The light that reaches us from distant galaxies has traveled across billions of years of spacetime, and by the time it reaches Earth, it has been stretched, redshifted, and distorted. However, by observing how light bends around a massive galaxy cluster acting as a lens, we can look deeper into the past. The farther we look into the universe, the younger the galaxies we observe. Gravitational lensing allows us to study galaxies in the early stages of their formation, closer to the time of the Big Bang, offering a unique glimpse into the conditions of the universe just a few 100 million years after its birth. This has massive implications for our understanding of galaxy formation and evolution. How did the first galaxies form? What was the environment like during the cosmic dawn, when the first stars began to light up the universe? Gravitational lensing, by allowing us to see these galaxies in such detail, is helping us answer these questions and deepen our understanding of the universe's earliest years. But there's even more potential hidden within the lens. As we look beyond the boundaries of our current technological capabilities, the possibilities become even more exciting. The new generation of space telescopes, like the James Webb Space Telescope, is expected to further enhance our ability to study gravitational lensing and its role in uncovering the universe's most elusive secrets. With the ability to observe the universe in infrared, Webb will be able to peer even further back in time, uncovering the formation of the first galaxies and providing deeper insights into the distribution of dark matter. One area where gravitational lensing could provide particularly exciting revelations is in the study of exoplanets. The detection of exoplanets, planets orbiting stars outside of our solar system, has exploded in recent years, with thousands of exoplanets discovered. Most of these discoveries have been made using methods like the transit method or the radial velocity method. However, gravitational lensing could open up new opportunities to study exoplanets in ways that other techniques cannot. When an exoplanet passes in front of a distant star, the planet's gravity can bend the light from the star, causing a temporary dimming or distortion of the star's light. This effect, known as gravitational microlensing, is incredibly subtle, but it can reveal the presence of a planet even if it is light years away. What makes gravitational microlensing particularly powerful is that it can detect exoplanets that are too faint to be observed using other methods. In fact, it could allow astronomers to find exoplanets that are located far outside the habitable zone of their stars, in environments where traditional detection methods would fail. In the coming years, gravitational microlensing could help us find more exoplanets than ever before, and it could even provide the first signs of habitable planets around distant stars. This would be a monumental discovery, further expanding our understanding of the potential for life beyond Earth. As we continue to unlock the mysteries of the universe, gravitational lensing will undoubtedly remain at the forefront of our exploration. Whether it's helping us study dark matter, explore the farthest reaches of the cosmos, or uncover the secrets of distant exoplanets, this phenomenon is one of the most powerful tools at our disposal. And as our technology and understanding continue to evolve, who knows what else we will uncover through the lens of gravitational lensing? Gravitational lensing is not just a phenomenon, it's a window into the deepest and most mysterious aspects of the universe. It's a reminder that the universe is vast, and that every new discovery leads to more questions, more puzzles, and more wonders. As we peer through this cosmic lens, we are not just observing the universe, we are part of an ongoing journey of discovery that has only just begun. The secrets of the universe are waiting to be revealed, and through the phenomenon of gravitational lensing, we are learning to see the universe in ways we never imagined possible. Who knows what we will discover next, but one thing is certain, the journey is far from over. Gravitational lensing's ability to alter the way we perceive the universe, stretching our understanding of physics, space, and time, is beyond profound. It's as if the very fabric of reality is being shaped by the presence of massive objects, bending the light that carries the story of the universe to our eyes. The more we explore this phenomenon, the more we realize how much it teaches us about not just the cosmos but the principles that govern it. To fully appreciate the implications of gravitational lensing, it's essential to dive deeper into its three main types: strong lensing, weak lensing, and microlensing. Each type reveals a unique aspect of the universe and offers different insights that are valuable to astronomers and physicists. Strong gravitational lensing. Strong lensing occurs when the mass of a galaxy or galaxy cluster is so great that it warps the light from a more distant object, like a background galaxy, so significantly that it creates multiple images or even rings. This phenomenon is often referred to as an Einstein ring, a name that pays homage to Albert Einstein, who first predicted the bending of light by gravity. In a strong lensing situation, the object acting as the lens is positioned almost perfectly along the line of sight between the observer and the distant source. As the light travels from the background galaxy, the foreground lens, due to its immense gravitational pull, bends the light rays. These bent rays then reach the observer, and in some cases, they form a complete ring around the lensing object. This ring is a direct result of the gravitational lensing effect, and it can be a powerful tool for astronomers. Einstein rings allow them to measure the mass of the lensing object with great precision, revealing hidden aspects of galaxies or clusters that would otherwise remain invisible. These rings can also serve as a magnifying glass, enabling us to observe the farthest reaches of the universe. Light that would have otherwise been too faint to detect is now magnified by the lensing effect, allowing astronomers to study distant galaxies in greater detail than ever before. This allows us to glimpse the early stages of galaxy formation and the dynamics of these ancient systems. Weak gravitational lensing. Weak gravitational lensing is the more subtle form of the phenomenon. Unlike strong lensing, which produces dramatic and easily noticeable effects like multiple images or rings. Weak lensing causes small distortions in the shapes of distant galaxies. While these distortions may seem almost imperceptible at first glance, over large surveys of galaxies, the collective effects can reveal profound insights about the mass distribution of the lensing object, such as a galaxy cluster or dark matter. With weak lensing, astronomers cannot see individual galaxies bending in significant arcs. Instead, they see a gradual stretching or elongation of the shapes of many galaxies due to the gravitational influence of mass on the light passing through it. These tiny distortions, when aggregated over vast numbers of galaxies, provide an indirect way of mapping the dark matter in galaxy clusters, helping to further our understanding of how this invisible mass is distributed. Weak lensing is incredibly important for understanding the large-scale structure of the universe, revealing how galaxies and dark matter interact on cosmic scales. For example, astronomers studying the cosmic web, a vast network of galaxies, gas, and dark matter, rely on weak lensing to map out the large-scale distribution of mass. By analyzing the subtle distortions of galaxy shapes, they can trace the underlying structure of the universe, including regions that are dominated by dark matter, which doesn't emit light or interact with electromagnetic radiation in the usual way. Gravitational microlensing. Gravitational microlensing is a fascinating variation of the lensing phenomenon, where the gravitational influence of a smaller object, such as a star or planet, causes a temporary increase in the brightness of a more distant star. In microlensing, the lensing object doesn't have to be a galaxy or a massive cluster of galaxies. It can be a single, relatively small object like a star or even a planet, whose gravity distorts and magnifies the light from a distant star behind it. Unlike the other types of lensing, which produce visible distortions in the shape of the lensed object, microlensing results in a brief, noticeable brightening of the distant star as the lensing object passes directly in front of it. This brief flash of light can last anywhere from a few hours to a few weeks, depending on the relative speeds of the lensing object and the background star. Astronomers use microlensing to detect objects that are otherwise undetectable, such as rogue planets, planets that don't orbit a star, but instead drift through space independently. These objects are difficult to detect through traditional methods, as they do not emit their own light. However, through microlensing, they can be detected when their gravitational influence magnifies the light from a distant star. Gravitational microlensing has revolutionized our understanding of exoplanets, as it provides a method for detecting planets that are far beyond the reach of traditional techniques, like the transit or radial velocity methods. By studying the microlensing events that occur in the Milky Way and beyond, astronomers are now able to identify thousands of exoplanets, some of which are located in environments previously considered unreachable. It has also been instrumental in expanding our knowledge of planetary systems in regions where stars and planets would otherwise remain invisible. The search for rogue planets, those mysterious worlds that are not bound to any star, has been particularly exciting. While it's incredibly difficult to detect such planets, gravitational microlensing provides a way to spot them based on their gravitational influence. In some cases, this has led to the discovery of planets that are not part of any stellar system, but instead wander the galaxy alone, perhaps with atmospheres and environments of their own. The role of gravitational lensing in dark energy. Another fascinating aspect of gravitational lensing is its connection to the study of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy accounts for roughly 68% of the total energy content of the universe, yet it remains one of the most perplexing and least understood phenomena in cosmology. Gravitational lensing plays a key role in the study of dark energy because it helps scientists measure the geometry of the universe with greater precision. When light from distant galaxies passes through the cosmic fabric, it is distorted by the matter that lies in its path. By studying these distortions, astronomers can trace the expansion of the universe over time, helping them understand the influence of dark energy on cosmic growth. This provides crucial data about the rate at which the universe is expanding and how dark energy is accelerating that expansion. Recent surveys, such as the Dark Energy Survey, use gravitational lensing to map out the distribution of matter in the universe, offering a clearer picture of how dark energy is affecting cosmic evolution. By observing the way light bends through massive objects, astronomers can refine their models of the universe's expansion, potentially unlocking new insights into the nature of dark energy itself. Gravitational lensing and the future of cosmology. The role of gravitational lensing in the future of cosmology is difficult to overstate. As new telescopes and observatories are developed, we will continue to push the boundaries of what we know about the universe. The upcoming James Webb Space Telescope, JWST for instance, is designed to observe the universe in infrared wavelengths, which will allow it to peer through dust clouds and observe distant galaxies with unprecedented clarity. Gravitational lensing will play a central role in the way JWST maps the universe. By using the lensing effect to magnify distant galaxies, the telescope will be able to study objects that were previously unreachable, unlocking new secrets about galaxy formation, dark matter, and dark energy. In the not-so-distant future, we may also see advancements in gravitational wave astronomy, an entirely new way of observing the universe. Gravitational waves, ripples in space-time caused by massive accelerating objects like black holes and neutron stars, will also help us understand the large-scale structure of the universe, and their interaction with gravitational lensing could provide further breakthroughs. Gravitational lensing, at its core, represents one of the most powerful tools available to astronomers today. It allows us to peer deeper into the universe than we ever thought possible, unlocking the mysteries of dark matter, dark energy, exoplanets, and the very fabric of space and time itself. As our technology and understanding continue to evolve, the potential for new discoveries is limitless, and the cosmic lens will continue to shape our view of the universe in exciting, unexpected ways. As we continue to explore the depths of gravitational lensing, one of the most profound implications of this phenomenon lies in the way it helps us probe the unseen and the unknown. The universe is far more mysterious than we could ever have imagined, and gravitational lensing plays a central role in revealing the invisible forces that shape it. Beyond simply providing a new way to observe distant galaxies and exotic objects, it is a key that unlocks some of the most fundamental mysteries of the cosmos. Mapping dark matter. Perhaps the most fascinating and transformative application of gravitational lensing is its use in the study of dark matter. This mysterious substance makes up about 85% of the mass of the universe, yet it does not interact with light in the way that ordinary matter does, making it invisible to traditional methods of observation. We know it exists because of its gravitational effects on galaxies and galaxy clusters, but its exact nature remains one of the biggest unsolved problems in astrophysics. Gravitational lensing offers a unique solution to this problem. By observing how the light from distant galaxies is bent as it passes through galaxy clusters, astronomers can map the mass distribution within those clusters, including the unseen dark matter. Dark matter, although invisible, has mass, and its gravitational influence bends light in much the same way as ordinary matter. This allows us to indirectly trace the presence of dark matter by studying the lensing effect it produces. When astronomers use gravitational lensing to map dark matter, they often find that the mass of a galaxy cluster is much greater than what is visible to the eye. The mass that we can see, the stars, gas, and other luminous matter, is only a fraction of the total mass. The remainder, invisible but inferred from gravitational lensing, must be made up of dark matter. This method has provided some of the clearest evidence for the existence of dark matter, and has helped refine our understanding of its distribution across the universe. We now know that dark matter is not evenly spread out but tends to cluster around galaxies and galaxy clusters, forming vast, invisible halos that influence the formation and evolution of galaxies. In fact, gravitational lensing is one of the best ways we have to study dark matter at large scales. By mapping the distortions in the light of background galaxies, scientists can pinpoint where dark matter is located and gain insights into how it behaves. These maps are crucial for developing new theories about dark matter's properties and how it interacts with other components of the universe, such as normal matter and dark energy. Gravitational lensing and galaxy formation. Gravitational lensing also provides a window into the past, allowing astronomers to look at galaxies as they were billions of years ago. When light from a distant galaxy is bent and magnified by a closer object, such as a galaxy cluster, it allows us to study the distant galaxy in much greater detail than we could with current technology. This has profound implications for our understanding of galaxy formation and evolution. The study of gravitational lensing can reveal the earliest stages of galaxy formation, long before the most distant galaxies could be detected using traditional observation techniques. By examining the light from distant galaxies that has been distorted and magnified by lensing, astronomers can study the formation of galaxies during the cosmic Dark Ages, a period roughly 200 million to 1 billion years after the Big Bang. These galaxies, which were formed when the universe was much younger, offer critical insights into how galaxies grow, evolve, and merge over time. In particular, gravitational lensing can help us answer key questions about galaxy mergers, a process that plays a fundamental role in galaxy evolution. When galaxies collide and merge, the resulting gravitational interactions can produce massive distortions in their structure, triggering bursts of star formation and leading to the growth of supermassive black holes. By observing galaxies that are being lensed by other objects, scientists can study these mergers up close, even if they are happening billions of light years away. This allows us to trace the evolution of galaxies from their earliest stages to the present day. Gravitational lensing and the search for exoplanets. In addition to its use in studying dark matter and galaxy formation, gravitational lensing has also become an essential tool in the search for exoplanets. These planets, which orbit stars outside our solar system, are often difficult to detect with traditional methods, especially if they are far from their parent stars or if they are in regions with high amounts of cosmic dust. However, gravitational lensing offers a powerful alternative. Gravitational microlensing, in particular, has proven to be a game-changer in the search for exoplanets. When a star passes in front of a more distant background star, the gravitational field of the foreground star can magnify the light from the background star, causing it to temporarily brighten. If the foreground star has one or more planets, the gravitational field of the planet can create additional distortions in the light curve, providing evidence of the planet's existence. This method has already led to the discovery of thousands of exoplanets, many of which are located in regions of the galaxy that would otherwise be difficult to study. Some of these planets are located in the so-called habitable zone of their parent stars, where conditions may be right for life to exist. The ability to detect exoplanets in this way is a major step forward in our quest to find potentially habitable worlds outside our solar system. Moreover, gravitational lensing allows astronomers to study these planets in more detail than would otherwise be possible. By analyzing the distortions in the light curve caused by gravitational microlensing, scientists can infer the mass, size, and composition of the exoplanet, as well as its distance from its parent star. This information is crucial for understanding the potential for life on other worlds and the conditions that might support it. Gravitational lensing and the fate of the universe. One of the most mind-boggling implications of gravitational lensing is its potential to help us understand the ultimate fate of the universe. The expansion of the universe is currently accelerating, driven by a mysterious force known as dark energy. Understanding how the universe is expanding and how its expansion will evolve over time is one of the most significant challenges in cosmology. Gravitational lensing plays a crucial role in this quest by allowing us to measure the rate of expansion with greater precision. By studying the way light is bent by massive objects, we can obtain detailed measurements of the distances to far-off galaxies and the speed at which they are receding from us. This data helps refine our understanding of the universe's expansion rate, which in turn provides valuable clues about the nature of dark energy. By combining this information with other observations, such as the cosmic microwave background radiation and galaxy redshift surveys, astronomers can begin to piece together a more complete picture of how the universe will evolve in the future. Will the expansion of the universe continue indefinitely, eventually tearing galaxies apart in a big rip? Or will gravity eventually slow the expansion and lead to a big crunch, where the universe collapses in on itself? These are questions that have puzzled scientists for decades, and gravitational lensing may hold the key to answering them. A new era of discovery. Gravitational lensing has already had a profound impact on our understanding of the universe, and its role in astronomy is only expected to grow as technology advances. New telescopes, such as the James Webb Space Telescope and the Vera C. Rubin Observatory, will allow us to observe gravitational lensing effects in greater detail than ever before. These observations will provide even more powerful insights into the nature of dark matter, dark energy, and the fundamental structure of the universe. As we continue to study the universe through the lens of gravity, we are not only expanding our knowledge of distant galaxies, but we are also expanding our understanding of the very fabric of space and time itself. Gravitational lensing has become a cornerstone of modern astronomy, and its potential for discovery is far from exhausted. With each new observation, we uncover new layers of the cosmos, pushing the boundaries of our knowledge and bringing us one step closer to answering the biggest questions in science. The story of gravitational lensing is not just a tale of bending light. It is the story of our quest to understand the universe on its deepest levels. As we peer through the cosmic lens, we are not just observers of distant galaxies, but active participants in unraveling the mysteries of the cosmos. In many ways, gravitational lensing is a reflection of our desire to understand the universe in all its complexity, an endeavor that is as boundless as the space it seeks to illuminate. As we continue to explore gravitational lensing, one of the remarkable aspects of this phenomenon is how it offers a glimpse into the very nature of light and space itself. It isn't just a tool for uncovering the hidden masses of dark matter or tracing the elusive contours of distant galaxies. It's a window into understanding the universe's most fundamental properties. Understanding the nature of space-time. One of the most intriguing things that gravitational lensing reveals is the way light interacts with the fabric of space-time. According to Einstein's theory of general relativity, mass and energy warp the space-time around them, creating a bending effect. This bending of space-time alters the path that light follows as it travels through the universe. What we are witnessing with gravitational lensing is the direct result of this warping. Light from distant stars or galaxies gets bent by the gravitational field of a massive object between us and the source. This effect is a profound confirmation of Einstein's prediction that space and time are not separate entities, but are intricately connected and can be distorted by mass. In a way, gravitational lensing serves as a natural experiment, allowing us to test and refine our understanding of general relativity. Each time we observe a gravitational lensing event, we get a clearer picture of how mass distorts the space-time continuum. As we observe more distant and more extreme objects, like black holes or clusters of galaxies, the bending of light can become more pronounced, providing us with even deeper insights into the workings of gravity on the grandest scales. The precise measurement of the way light is bent also helps in refining the fundamental constants of physics. Scientists can use lensing to probe the curvature of space and time and better understand how gravity behaves in the presence of extremely massive objects. This could provide new clues about the behavior of gravity in different conditions, particularly in the presence of extreme objects like black holes and neutron stars, where the curvature of space-time is most extreme. Gravitational lensing as a tool for measuring the universe's structure. Another fascinating application of gravitational lensing is its role in mapping the large-scale structure of the universe. The distribution of galaxies, clusters, and superclusters across the universe is not uniform. Instead, it forms a complex web-like structure, with massive galaxy clusters acting as nodes in the web. By studying the way light is bent as it travels through these structures, scientists can learn more about how the universe is organized on its largest scales. In a sense, gravitational lensing gives us a direct way of mapping the universe. When light from a distant source passes through a galaxy cluster, the bending of that light provides us with valuable information about the cluster's mass, its density, and its distribution in space. By observing multiple lensing events and comparing how the light from distant galaxies is distorted, astronomers can begin to chart the large-scale structure of the universe in unprecedented detail. This mapping process is particularly important for studying the mysterious phenomena that shape the universe on its largest scales. Gravitational lensing allows scientists to study the distribution of dark matter and how it influences the formation and evolution of large-scale structures like galaxy clusters and superclusters. It also helps us understand how these structures evolve over time and how they interact with the cosmic fluid of dark energy that drives the accelerated expansion of the universe. Through gravitational lensing, astronomers are also learning more about the history of the universe's expansion. The lensing effect is not just a static snapshot of the present, but also a tool that allows us to look back in time. Since light takes time to travel across the vast distances of the cosmos, the light we see from distant galaxies today has often been traveling for billions of years. This allows gravitational lensing to provide a time capsule of sorts, revealing the state of the universe when the light we are now observing was first emitted. The future of gravitational lensing observations. Looking to the future, the study of gravitational lensing is poised to expand dramatically. Upcoming telescopes, like the James Webb Space Telescope, JWST, and observatories like the Vera C. Rubin Observatory are going to provide a wealth of new data that will allow astronomers to study gravitational lensing on an unprecedented scale. The ability to observe more distant galaxies and more lensing events will vastly increase our knowledge of the universe, helping us to piece together the mysteries of dark matter, dark energy, and the large-scale structure of the cosmos. The JWST, in particular, will be able to observe the most distant objects in the universe, many of which are so far away that they are not visible with current technology. When these galaxies are lensed by foreground objects, the magnifying effect will allow scientists to study their structure, composition, and even their early stages of formation. This will provide new insights into the birth and evolution of galaxies, stars, and planetary systems, and help us understand how the first galaxies in the universe were formed. In addition to the technological advancements that are coming in the field of gravitational lensing, new theories are also being developed to refine our understanding of the phenomenon. One area of active research is the study of strong gravitational lensing, where the bending of light is so pronounced that multiple images of a single object can be seen. These multiple images allow scientists to measure not only the distribution of mass in the foreground lensing object but also the geometry of space-time itself. Moreover, as gravitational lensing continues to play a critical role in the search for dark matter and dark energy, it could provide the breakthrough that scientists have been hoping for. By mapping the unseen matter in the universe, astronomers can begin to answer the long-standing questions about the true nature of these mysterious substances. Will we eventually uncover the elusive particles that make up dark matter, or will we discover entirely new forms of matter that we never even imagined? The answers to these questions could dramatically reshape our understanding of the universe and our place in it. Gravitational lensing and the search for the unknown. While we have made incredible strides in understanding the fundamental workings of gravitational lensing, there is still much to uncover. As more lensing events are observed and analyzed, we will continue to discover new phenomena that we never expected. Gravitational lensing has already revealed strange, previously hidden objects, such as black holes that are in the process of devouring stars, and distant galaxies that appear to be warped beyond recognition. These discoveries serve as a reminder of just how much we still have to learn about the universe. The more we observe, the more we realize how much is still out there, beyond our current reach. Every time we peer through a gravitational lens, we are not just learning about distant galaxies, dark matter, or the laws of physics. We are opening a door to the unknown, pushing the boundaries of human knowledge to new, unimaginable heights. In many ways, gravitational lensing is the ultimate cosmic detective tool. It allows us to investigate the universe's most puzzling questions, offering clues to some of the most significant mysteries in science. It is a reminder that even though we have come far in our understanding, the universe is still full of surprises, waiting to be discovered through the incredible power of light, gravity, and curiosity. Gravitational lensing has already transformed our view of the cosmos, and as we continue to explore its mysteries, it will undoubtedly lead to even more groundbreaking discoveries. Whether we're mapping the distribution of dark matter, uncovering the secrets of galaxy formation, or searching for habitable exoplanets, gravitational lensing will remain a key tool in our ongoing quest to understand the universe. And as we look deeper into space, we can only wonder what new, mind-bending discoveries lie just beyond the horizon, waiting to be revealed by the bending of light and the distortion of space-time. As we continue to delve into the implications of gravitational lensing, it becomes clear that its power goes beyond just enhancing our understanding of galaxies, dark matter, and cosmic structures. This phenomenon is one of the primary tools astronomers use to observe the universe in ways that were once thought impossible. And as we develop new techniques and technologies, we will continue to push the boundaries of what gravitational lensing can reveal. Gravitational lensing and the search for exoplanets. One of the more recent and exciting applications of gravitational lensing is in the search for exoplanets, especially those that lie beyond our direct line of sight. Traditionally, exoplanet detection relies on methods such as the transit method, where scientists observe a planet passing in front of its parent star, or the radial velocity method, which measures the star's slight wobble due to the gravitational pull of a planet. However, gravitational lensing offers a completely different approach, particularly useful for detecting exoplanets orbiting distant stars. When a star with an exoplanet passes directly in front of another more distant star, the light from the background star can be gravitationally lensed. This creates a temporary, brightening effect that can be detected by astronomers. This technique is known as microlensing. While the event is brief, lasting only a few days to weeks, the gravitational lensing effect can reveal the presence of planets that are otherwise undetectable by other means. The brightness of the lensing effect is not only dependent on the mass of the star but also on the mass of the planet. The larger the planet, the more noticeable the lensing effect. Microlensing has already been used to detect exoplanets, but it is still a relatively new technique and one that needs to be refined and expanded. It also holds the potential to uncover many more planets in the farthest reaches of the galaxy, particularly those that are small, rocky, or orbit in the habitable zone of their stars, regions where life might be possible. Since gravitational lensing can probe distant stars and their planetary systems, it opens up new possibilities in the search for extraterrestrial life. The role of gravitational lensing in dark matter research. Gravitational lensing is arguably one of the most valuable tools in the hunt for dark matter. Dark matter remains one of the greatest mysteries in modern astrophysics, as it cannot be seen directly through traditional means. Yet we know it exists because of its gravitational effects on visible matter. Gravitational lensing provides a way to study dark matter indirectly. When a massive galaxy cluster acts as a gravitational lens, it bends and distorts the light coming from more distant galaxies. By studying these distortions, astronomers can infer the mass distribution of the galaxy cluster, which includes not only visible matter like stars and gas but also dark matter. The effects of gravitational lensing often reveal that much of the mass in galaxy clusters is made up of dark matter, as it accounts for the majority of the lensing effect. Without gravitational lensing, much of the dark matter would remain hidden from us, making it much harder to study. Scientists can use gravitational lensing to trace the distribution of dark matter across the universe, potentially allowing us to learn more about its composition, its role in the formation of cosmic structures, and even the fundamental nature of the mysterious particles that constitute it. In some cases, the distortions caused by gravitational lensing can even help identify dark matter clumps or filaments that were previously undetectable. As observational technology continues to improve, especially with the upcoming launch of next-generation telescopes, gravitational lensing will remain one of the most powerful methods to study dark matter on a large scale. In fact, it might even help solve the ultimate question: what is dark matter, and how does it interact with normal matter? Uncovering the cosmic web, gravitational lensing as a tool for understanding large-scale structure. The large-scale structure of the universe, often referred to as the cosmic web, is a vast, complex network of galaxies, galaxy clusters, and vast voids. These structures form a web-like pattern, with galaxies and clusters of galaxies connected by vast, thread-like filaments of dark matter and gas. Understanding how this cosmic web formed and how it continues to evolve is one of the greatest challenges in modern cosmology. Gravitational lensing plays a crucial role in mapping this web and gaining insights into the forces that shaped it. By studying how light is bent as it passes through different parts of the cosmic web, scientists can determine the density and distribution of matter along the line of sight. The bending of light can reveal how galaxies and clusters are connected through dark matter filaments, and it can even give us a clearer picture of how large-scale structures are growing and evolving over time. Gravitational lensing thus helps build a more complete picture of the universe's structure, showing us not just isolated objects, but also the grand tapestry that connects them. The study of the cosmic web is important for understanding the evolution of galaxies, star formation, and the role of dark energy in accelerating the expansion of the universe. Gravitational lensing is one of the few tools that allows astronomers to probe these vast cosmic structures in such detail. Gravitational lensing in the search for the edge of the universe. One of the more exciting prospects in the field of gravitational lensing is its potential for helping us explore the farthest reaches of the universe. Because gravitational lensing allows us to observe objects that are behind other, more massive objects, it provides a method for looking beyond the observable universe. Essentially, it can serve as a cosmic magnifying glass, allowing us to observe galaxies and other celestial objects that are so far away that their light is barely reaching us. Through gravitational lensing, astronomers have already been able to observe galaxies that formed just a few 100 million years after the Big Bang. These early galaxies provide crucial information about the conditions of the universe in its infancy. But lensing could also allow us to see even further back, possibly providing glimpses of the universe before the first stars and galaxies formed. This ability to peer deeper into the cosmos and observe distant objects is vital for answering fundamental questions about the origins of the universe, the formation of galaxies, and the evolution of cosmic structures. Gravitational lensing might hold the key to unlocking the mysteries of the universe's early history and providing a deeper understanding of its future. The incredible precision of gravitational lensing observations. The study of gravitational lensing requires an extraordinary level of precision. When we observe a gravitational lensing event, we are measuring incredibly small distortions in the shape of light from distant galaxies, distortions that can be as small as a fraction of a pixel on a camera's sensor. This demands the most sensitive instruments and cutting-edge technology. In recent years, astronomers have developed highly sophisticated methods for analyzing gravitational lensing data. For instance, the Hubble Space Telescope has been instrumental in capturing some of the most detailed images of gravitational lensing, providing precise measurements of the lensing effect in distant galaxy clusters. New techniques, such as weak gravitational lensing, are also pushing the boundaries of what we can observe. These methods measure smaller distortions, allowing us to create high-resolution maps of the mass distribution in galaxy clusters and large-scale structures. The upcoming James Webb Space Telescope, JWST, is expected to significantly advance gravitational lensing studies. With its powerful infrared capabilities, it will allow astronomers to study lensing events that are beyond the reach of current optical telescopes. This will open up new opportunities for understanding the most distant galaxies, black holes, and other celestial objects, and will undoubtedly lead to groundbreaking discoveries. The big picture. Gravitational lensing as a gateway to the unknown. As we've seen, gravitational lensing is an incredibly powerful tool that is expanding our understanding of the universe in profound ways. It's helping us map dark matter, uncover the secrets of distant galaxies, search for exoplanets, and explore the very structure of the cosmos itself. But perhaps the most exciting aspect of gravitational lensing is that it is continually revealing new mysteries and unanswered questions. Gravitational lensing doesn't just give us a better view of the universe. It challenges our understanding of the universe itself. It shows us that light, mass, and space are more interconnected than we ever imagined. It's a reminder that, while we've come a long way in understanding the cosmos, there's still so much more to learn. Each new lensing event is like a new chapter in an ongoing story of discovery, one that is sure to keep us captivated for generations to come. So, as we look deeper into space, powered by the lensing of light and the bending of space-time, we are bound to discover even more about the universe, its past, present, and future. With each breakthrough, gravitational lensing brings us closer to the answers we seek, shedding light on the darkest corners of the cosmos. Gravitational lensing remains one of the most remarkable phenomena in our universe, serving as a cosmic tool that allows us to see things that would otherwise be invisible. By bending light through the powerful influence of gravity, it provides astronomers with the ability to probe the furthest reaches of space and uncover secrets that are otherwise hidden from our view. As technology advances and our ability to detect faint light grows more sophisticated, gravitational lensing will only become a more indispensable tool in the search for cosmic answers. The future of gravitational lensing observations. The next steps in the study of gravitational lensing are poised to be transformative. With advancements in telescope technology, our ability to capture more detailed and precise lensing events will open up new possibilities for understanding the universe. One of the most anticipated telescopes in this regard is the Nancy Grace Roman Space Telescope, set to launch within the next few years. This new observatory will be specifically designed to take advantage of the gravitational lensing effect, providing astronomers with an unprecedented ability to map the large-scale structure of the universe and detect faint objects that would otherwise be invisible. The Roman Space Telescope will be able to measure the tiny distortions caused by weak gravitational lensing across vast regions of the sky. This will allow scientists to conduct more detailed surveys of galaxy clusters, study the distribution of dark matter, and investigate the role of cosmic evolution in the formation of the universe's largest structures. Its high-resolution imaging and wide-field surveys will provide a clearer picture of the cosmic web, helping us better understand how galaxies, clusters, and even dark matter interact on an immense scale. But even before the Roman Space Telescope takes to the skies, existing instruments such as the Hubble Space Telescope continue to make groundbreaking discoveries. One of the incredible things about gravitational lensing is that it can be observed not just in distant galaxies but also within our own galaxy, the Milky Way. This is particularly true for strong gravitational lensing events, where light is bent in more extreme ways. These observations are revealing details about black holes, supernovae, and other exotic phenomena that might otherwise be hidden in the vastness of space. As we develop more powerful tools for capturing lensing events, the possibility of detecting and studying exoplanets, rogue planets, and distant galaxies will become more attainable. Through gravitational lensing, we can essentially zoom in on distant objects, gaining a detailed look at their properties without ever needing to travel vast distances. This breakthrough technique is one of the most promising methods for expanding our knowledge of the universe and could pave the way for even more discoveries in the coming years. Gravitational lensing in the search for the first galaxies. Perhaps one of the most exciting future prospects for gravitational lensing is the study of the first galaxies that formed after the Big Bang. The earliest galaxies in the universe are incredibly distant, and their light has taken billions of years to reach us. Observing these galaxies directly is extremely challenging because their light is faint and stretched out due to the expansion of the universe. However, gravitational lensing acts like a magnifying glass, allowing us to peer deeper into the universe's history and observe galaxies that formed just a few 100 million years after the Big Bang. By studying these distant galaxies, astronomers hope to uncover information about the conditions that led to the formation of galaxies, stars, and other cosmic structures. These observations will help us understand how the universe evolved in its earliest stages and give us insights into the mysterious processes that led to the creation of the first stars and galaxies. Gravitational lensing will be crucial in this endeavor, allowing us to detect these galaxies with much greater sensitivity than would otherwise be possible. The mysteries of the universe still to be uncovered. As incredible as the discoveries of the past few decades have been, the universe remains a vast, mysterious place, full of unsolved questions and phenomena that challenge our understanding. Gravitational lensing has already revealed a tremendous amount about dark matter, the large-scale structure of the universe, and the evolution of galaxies, but there are still many unanswered questions waiting to be explored. Some of these mysteries might even be waiting for us to unlock them through the study of gravitational lensing itself. One of the big questions still on the horizon is the true nature of dark energy. Dark energy is the force that is driving the accelerated expansion of the universe, but its origins and properties remain elusive. Some scientists believe that dark energy may interact with gravity in ways we don't fully understand, and gravitational lensing could play a crucial role in uncovering more about this mysterious force. For example, by observing how gravitational lensing behaves across vast stretches of space, we could learn more about the influence of dark energy on the fabric of spacetime itself. Additionally, gravitational lensing may help shed light on the true nature of black holes. While we've already made great strides in understanding these enigmatic objects, much about them remains a mystery. Gravitational lensing can help reveal the behavior of matter around black holes, the way they interact with their surroundings, and how they shape the space around them. These observations are critical for understanding how black holes evolve over time and how they might influence the formation of galaxies and other cosmic structures. As we continue to explore the universe with the help of gravitational lensing, we may also uncover new and unexpected phenomena. The universe is vast and unpredictable, and the more we learn, the more we realize how much we have yet to discover. Gravitational lensing is a crucial tool in this ongoing exploration, allowing us to unlock the secrets of the cosmos and answer questions that have puzzled humanity for centuries. A window into the future. Looking ahead, the role of gravitational lensing in shaping our understanding of the universe cannot be overstated. As new technologies emerge and our observational capabilities continue to improve, the possibilities for discovering new galaxies, exoplanets, and cosmic structures are limitless. From the discovery of the first galaxies after the Big Bang to the detection of hidden dark matter and the exploration of distant black holes, gravitational lensing is poised to revolutionize our understanding of the universe in ways we are only beginning to grasp. What's even more fascinating is that we have only begun to scratch the surface of what gravitational lensing can tell us. Every new observation opens the door to further questions and deeper mysteries, ensuring that the study of lensing will remain a vibrant and essential part of astrophysical research for decades to come. The more we learn about how gravity warps light, the more we understand how the universe itself works. And in doing so, we are unlocking the fundamental secrets of existence, secrets that will continue to captivate and inspire humanity for generations. The universe is a grand and beautiful puzzle, one whose pieces are slowly being revealed through the lens of gravitational lensing. With each new discovery, we come closer to understanding the true nature of the cosmos, and with each new breakthrough, we remind ourselves that we are only beginning to understand the vastness and complexity of the universe in which we live. The journey of exploration is ongoing, and gravitational lensing is one of the most important keys to unlocking the mysteries of space. Gravitational lensing isn't just a theoretical tool used by astronomers. It is a fundamental aspect of how we observe the universe. It is a reminder of how spacetime, once thought to be a fixed backdrop, is actually a dynamic and malleable stage, one where gravity can shape and distort the very fabric of reality. The study of this phenomenon has already yielded groundbreaking results, but as our observational capabilities improve, gravitational lensing will continue to offer us deeper insights into the nature of the cosmos. The role of gravitational lensing in cosmology. One of the key fields where gravitational lensing has made a significant impact is cosmology. Cosmology is the study of the origins, structure, and eventual fate of the universe. By using gravitational lensing to map the distribution of mass across the cosmos, astronomers can gain insight into the large-scale structure of the universe, as well as how it has evolved since the Big Bang. Through weak gravitational lensing, researchers have been able to map the cosmic web of dark matter that permeates the universe. This cosmic web is made up of vast filaments of dark matter that connect galaxies, galaxy clusters, and other structures. Even though dark matter cannot be directly observed, its influence is detectable through the way it bends light. By studying how light from distant objects is distorted by these massive cosmic structures, we can see where dark matter exists and map its distribution across the universe. This work is crucial for understanding the expansion of the universe, how galaxies form, and the role that dark energy plays in driving the accelerated expansion of the cosmos. Weak lensing also helps us understand the overall geometry of the universe, giving us a clearer picture of whether the universe is flat, open, or closed. Such insights are fundamental for refining models of the universe's past and future, and are essential for answering the most profound questions in cosmology. Gravitational lensing and the search for exoplanets. The application of gravitational lensing has also extended to the search for exoplanets, which are planets orbiting stars outside of our solar system. while astronomers have developed many techniques for detecting exoplanets, such as the transit method, where a planet passes in front of its star, and radial velocity, where the star's movement is affected by the gravitational pull of an orbiting planet. Gravitational lensing offers a unique opportunity for detecting exoplanets that would otherwise be impossible to find. This method is known as gravitational microlensing, and it occurs when a star, or any compact object, like a planet, passes in front of a more distant background star. The gravitational field of the foreground object acts like a lens, magnifying the light from the background star. This can reveal the presence of a planet orbiting the foreground star, even if that planet does not emit any detectable light. Microlensing is particularly useful because it can detect planets at much greater distances than other methods and can also detect planets that are not emitting their own light, such as those that may be too small or too far away to be observed directly. The discovery of new exoplanets via gravitational microlensing has already led to some intriguing findings. For example, in 2011, astronomers detected a planet using this technique that was about 25,000 light-years away from Earth. The potential for future discoveries is immense, especially as our observational tools improve, and as we learn to identify even more faint and distant planets. This method could even reveal rogue planets, planets that have been ejected from their original star system and are now drifting through interstellar space. How gravitational lensing illuminates the hidden universe. One of the most fascinating aspects of gravitational lensing is its ability to reveal objects that are otherwise hidden from view. For instance, by using gravitational lensing, astronomers can observe distant galaxies and objects that are billions of light-years away. The immense gravity of galaxy clusters bends the light emitted from these galaxies, essentially acting as a magnifying lens, bringing them into clearer view. This method allows us to observe galaxies in the very early stages of their formation, providing a glimpse into a time when the universe was much younger. Additionally, gravitational lensing can also expose hidden black holes, which are otherwise invisible because they do not emit light. When light passes near a black hole, it bends and distorts, producing lensing effects that can reveal the presence of these otherwise elusive objects. By studying the way light is bent around suspected black holes, astronomers can gather critical information about their mass, spin, and other characteristics. This process is crucial in the ongoing study of the supermassive black holes that reside at the centers of galaxies. Understanding these black holes is vital for understanding how galaxies themselves evolve. For example, supermassive black holes are believed to have played a key role in the formation and growth of galaxies, and the gravitational lensing of light near these black holes offers a unique window into their properties and behavior. The connection between gravitational lensing and dark matter. Dark matter is one of the greatest mysteries in modern physics. Despite making up approximately 27% of the universe's total mass and energy, dark matter cannot be directly observed, as it does not emit, absorb, or reflect light. However, its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Gravitational lensing plays a crucial role in this process. By observing how light is bent around galaxy clusters, scientists can map the distribution of dark matter within these clusters. This method of detecting dark matter is known as weak gravitational lensing. When light from distant galaxies passes through a cluster of galaxies, the gravitational pull from the cluster bends and distorts the light. This distortion allows astronomers to map out the dark matter in the cluster, which would otherwise be invisible. Understanding the distribution of dark matter is essential for understanding how galaxies and galaxy clusters form and evolve. Dark matter is thought to provide the gravitational pull necessary to hold galaxies and clusters together, preventing them from flying apart due to the force of their own motion. Without dark matter, galaxies and clusters would not be able to form in the way they do, and the large-scale structure of the universe would look very different. Gravitational lensing and the evolution of the universe. The study of gravitational lensing also has profound implications for understanding the history of the universe. By analyzing the way light is bent by massive objects, scientists can determine the age of certain structures and track how they have evolved over time. This is particularly important when studying the early universe, as gravitational lensing allows us to observe galaxies and stars that formed only a few 100 million years after the Big Bang. The lensing of light by galaxy clusters also provides important insights into the evolution of these clusters themselves. By studying the distortions caused by these massive structures, astronomers can learn how they formed, how they grew, and how they continue to evolve. This information helps to refine our models of cosmic evolution, shedding light on the fundamental processes that have shaped the universe over billions of years. Gravitational lensing and the future of space exploration. Gravitational lensing is not just a tool for astronomers looking at distant galaxies. It's a fundamental part of the future of space exploration. With missions like the James Webb Space Telescope, which is set to revolutionize our understanding of the universe, and the Nancy Grace Roman Space Telescope, gravitational lensing will play a key role in the next wave of discoveries. These telescopes, along with future observatories and missions, will help expand our knowledge of the cosmos in ways we have yet to fully imagine. In the coming decades, we can expect to see more detailed observations of distant objects, including galaxies that existed at the very beginning of the universe. We'll also see more discoveries related to dark matter, dark energy, and black holes, phenomena that continue to elude scientists despite decades of study. Gravitational lensing, in all its forms, will be an essential tool for these future discoveries, opening doors to new realms of understanding that will shape our conception of the universe for generations to come. Gravitational lensing is far more than just a phenomenon we observe in the sky. It is a window into the universe's deepest secrets. Through the bending of light by massive objects, we can explore the farthest reaches of space and time, uncover hidden phenomena, and gain insight into the nature of gravity, dark matter, and dark energy. As our technology advances, gravitational lensing will continue to serve as a powerful tool for unlocking the mysteries of the cosmos, allowing us to peer into the past, present, and future of the universe. The study of gravitational lensing is an ongoing journey, one that will continue to shape our understanding of the cosmos for years to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.